You know, think about making a Bitcoin payment.
Hmm.
Fast, cheap, like sending an email. Anywhere, instantly.
Great.
That's always in the dream, right?
Absolutely. But for a long time, the reality, it felt a bit, well, slower. Much slower.
Okay, let's unpack this because today we're doing a deep dive into two seemingly small changes in Bitcoin's history, BIP-68 and BIP-112.
Yeah, they sound kind of like technical jargon, maybe alphabet soup.
Right, but honestly, these little upgrades, they quietly unlock the potential for the Lightning Network. And, this whole new world of faster, cheaper Bitcoin transactions happening off the main network.
And what's really fascinating, I think, is that these weren't like traumatic, super controversial overhauls. Not at all. No, they were more like carefully designed building blocks, Lego bricks maybe, that just fit perfectly into the existing structure.
Ah, okay. So we're going to explore how these upgrades solve some really fundamental limits in Bitcoin's original design.
Exactly. And the interesting journey they took to actually become part of the system, the governance, and the truly revolutionary impact they've had.
Right. So think of this as your quick guide, understanding how Bitcoin, which, initially had a bit of a transaction traffic jam, how it evolved into a platform that could potentially handle global payments.
Yeah.
And crucially, without sacrificing its core strengths.
Things like that ironclad security and, staying truly decentralized, that's key.
So our mission today is basically to get exactly how these foundational upgrades pulled off that transformation and why it matters so much for Bitcoin's future, potentially as a global payment system.
And we'll be drawing from, the actual discussions and explanations around these Bitcoin improvement proposals themselves, the source material.
Okay, ready to see how these pieces fit together?
Let's do it. So maybe start with the puzzle Bitcoin was facing back then.
Yeah, what is the big challenge?
Well, around 2015 or so, it was becoming really clear the network had a scaling problem, a bottleneck. The way it was designed, with that limit on the size of transaction blocks, it just meant it could only process a few transactions per second. Globally.
Not nearly enough for mass adoption, obviously.
Not even close.
No.
And the idea of just making the blocks bigger, well, that was debated.
The block size war, yeah.
But it brought its own set of problems. It could potentially make it harder, more expensive for just regular users to run a full Bitcoin node.
Which hurts decentralization, a core principle.
Precisely. So it was like having, a highway with a great speed limit, but only one lane.
Good analogy. So the community started looking elsewhere, layer 2.
Exactly. Exploring these layer 2 solutions, new technologies built on top of the Bitcoin network.
And Lightning emerged from that.
Yeah, the Lightning Network emerged as a really, really exciting idea. A way for people to transact directly with each other off the main blockchain.
And only settle up kind of on the main chain later.
Right, just record the final balances occasionally, much more efficient. And here's where it gets really interesting. There was a fundamental technical roadblock.
Okay.
Well, the magic of Lightning, it relies on users creating these secure payment channels directly between themselves, right? These channels allow for those instant transactions, but they also need ways to prevent cheating and ensure that if something goes wrong or someone disappears, there's a fair way to resolve it. A fallback.
Makes sense.
And this is where Bitcoin's scripting language, its way of doing basic smart contracts was, limited at the time. It just lacked a reliable way to enforce conditions based on time, specifically time relative to certain transactions happening.
Okay, so before these BIPs, BIP-68 and 112, what exactly couldn't Bitcoin script do? What was holding back Lightning?
The big limitations were all around how time could be specified and, crucially, checked within the scripts.
Okay.
So first, there just wasn't a secure way to say, look, this Bitcoin output, this UTXO, it can't be spent until a certain amount of time has passed since a specific event happened.
Like relative time.
Exactly, relative time. Bitcoin did have this feature called nLockTime.
Right, I've heard of that.
Yeah, it lets you say an output can't be spent until a specific future block number or a specific clock time, an absolute point in the future. But for something like a Lightning channel dispute, you need to say, this money can't be touched for, let's say, 100 blocks after this channel closing transaction was broadcast. That relative aspect, timing things based on prior events, that was the missing piece.
Got it.
Yeah.
So like you said before, it could set a future alarm clock maybe, but not a stopwatch that starts running after something else happens.
That's a perfect way to put it. And the second crucial limitation was that there wasn't a way for the script itself to verify that these time-based conditions had actually been met.
Oh, interesting.
Even if you could somehow set a relative time limit, there wasn't a built-in check within the script to say, okay, has this time limit expired? If not, this path, this outcome shouldn't happen.
And that was critical for things like dispute periods and off-chain contracts.
Absolutely critical. You need that enforcement mechanism within the contract rules themselves.
Okay, so enter BIP-68. How did that tackle the first problem, the need for relative time locks?
Right. So BIP-68, which was proposed by Mark Friedenbach, came up with this really clever way to repurpose an existing part of Bitcoin transactions.
Which part?
It's called the sequence number, or nSequence. It's a field in every transaction input.
Okay. Was it being used much?
Not really, not reliably anyway. Originally, it was kind of intended for a feature called replace by fee.
RBF.
Yeah, but it wasn't widely adopted back then, mainly because of how miner incentives worked out. It was sort of underutilized space.
So BIP-68 gave it a new job.
Pretty much. For transactions marked as version 2 or higher, that was the opt-in mechanism. BIP-68 gave this nSequence field a new, agreed-upon meaning. It became a way to specify a delay relative to when the previous transaction, the one this input is spending, was confirmed on the blockchain.
Ah, okay. Like giving an old tool a brand new, very specific purpose. So instead of just can't use until block 800,000, it can now say can't use for 100 blocks after the transaction creating this coin was confirmed.
Exactly. And that's a fundamental shift for building these kinds of off-chain protocols, right?
Huge. It feels like the key ingredient that was missing.
It really was. And BIP-68 has some nuances too. Like the very first bit 31 of that nSequence number, it acts like a disable flag.
An off switch.
Yeah, basically. If that bit's set, the relative lock time feature is turned off for that input. Keeps options open for future uses too. And there was another bit 22, that let you choose the units. Do you want to count the relative time in blocks or in chunks of time, specifically 512-second intervals?
So flexibility in how you measure the delay.
Right. And there was a limit. The value itself is only 16 bits, so the maximum relative delay you could set was around 65,535 blocks or time intervals, which works out to roughly a year.
Okay, a decent time frame for most contracts, I imagine.
Usually, yeah. And one last detail. These rules didn't apply to Coinbase transactions, the ones that create new Bitcoin in each block.
Got it. Okay, so BIP-68 gives us the ability to set these relative time locks. But how did Bitcoin actually enforce them? Like in a smart contract way? That sounds like where BIP-112 comes in.
Exactly right. So BIP-112, which was really championed by BTC Drac and Eric Lombroso, introduced a new instruction, a new opcode for Bitcoin scripts. It's called OP Check Sequence Verify.
Or CSV for short.
CSV, yeah, much easier to say. Now, to make sure this change was a soft fork compatible with older Bitcoin software.
Right. Super important for Bitcoin upgrades.
It's crucial. This new ability was cleverly added by redefining an existing opcode called OP and OP3. NOP just means no operation, basically do nothing.
So older nodes that didn't know about CSV would just see OP and OP3 and ignore it.
Precisely. They just carry on validating the transaction according to the rules they know. The network keeps running smoothly. It's like adding a secret handshake. Like you said, people who don't know it just see a regular handshake.
Okay, very clever. So what does OP Check Sequence Verify, or CSV, actually do when a new updated node encounters it?
So CSV lets a Bitcoin script check if the relative time lock that was set using BIP-68 in that nSequence field of the input being spent has actually been satisfied, has enough time passed. When a script hits this CSV instruction, it looks at the top item on its data stack that's expected to be the desired minimum relative lock time value. And it compares that value to the actual nSequence field of the input.
So it's checking the requirement against the reality.
Exactly. And it performs a few checks. The script will fail, meaning the transaction is invalid if, say, the stack is empty or the value it's checking is negative.
Right.
Or if the special disable flag in the nSequence field is not set, and any of these are true. The transaction version is less than 2, or the input sequence disable flag is set, or the time units don't match between the script value and the nSequence value, or the required time from the script is actually greater than the time specified in the nSequence.
Wow, okay, that's a lot of conditions.
Yeah.
But the core idea is compare the required wait time from the script with the actual time conditions set on the input using BIP-68.
That's the heart of it. If the required relative time, according to the nSequence field, hasn't passed yet compared to the value the script provides, CSV makes the script fail. Transaction invalid.
But if enough time has passed?
Then CSV basically does nothing. It acts like the original OP and OP, and the script execution just continues on to the next instruction.
Okay, so these two pieces work together beautifully. BIP-68 sets the relative time condition in the nSequence field, and BIP-112, CSV, provides the script level tool to check if that condition has been met.
You got it. And that combination is what unlocked the ability to create things like Lightning's hashed time-locked contracts, HTLCs, and those secure channel closures with agreed-upon waiting periods or dispute windows.
Right, the core mechanisms of Lightning.
Think about that Lightning channel again between Alice and Bob. They can now craft transactions where, say, Alice gets paid if she reveals a secret within 48 hours.
Okay.
But if she doesn't, and then some additional time passes the dispute period, Bob can securely get his funds back.
How do the BIPs enable that?
Well, BIP-68 allows that 48 hours later, or 100 blocks later, part to be defined relative to when the channel state is broadcast. And BIP-112, the CSV opcode, allows the script to enforce it. Has the 48-hour window passed? If yes, check Alice's secret claim. If not, has the longer dispute window passed? If yes, let Bob reclaim.
Gotcha. So you can have these branching conditions based on time.
Exactly. That fundamental ability, having both time-based expirations and immediate conditional paths based on things like signatures or revealed secrets that became the bedrock, the foundation for making the Lightning Network work securely and without needing to trust the other person.
Okay, technically that sounds like a massive leap forward. Solves a huge problem. But, just writing the code isn't enough in Bitcoin, is it? What were some of the real-world hurdles in actually getting these changes implemented, agreed upon, activated across the whole network?
Oh, you're absolutely right. It's never just about the code. In a decentralized system like Bitcoin, changing the core rules, the consensus rules, is a complex dance. Ensuring the safety of the soft fork was paramount. Like we touched on, any change, like adding CSV, needs to be done so it doesn't accidentally invalidate old blocks or confuse the thousands of nodes out there that might not upgrade immediately.
Backwards compatibility is king.
It has to be. So that clever repurposing of the nSequence field and redefining OP and OP3 using specific version numbers and flags as triggers, that was all designed to achieve this soft fork safety. Older nodes could still relay and generally process these new style transactions, even if they didn't fully enforce the CSV rule themselves.
You wouldn't see them as invalid, just different.
Exactly. It's like, everyone agrees on a new grammar rule. People who haven't learned it yet can still understand the basic sentences, even if they miss the nuance.
Okay. What else? Complexity.
Definitely script complexity. These new time-based rules had to play nicely with all the existing features of Bitcoin's script language.
Yeah.
CSV had to interact perfectly with the stack-based processing without opening up weird edge cases or security holes.
Sounds like a testing nightmare.
Oh, it required a massive amount of careful design, rigorous peer review by tons of different developers looking at it from all angles, and just extensive testing. They had to try and break it in every way imaginable.
Trying to think like an attacker.
Absolutely. Especially in adversarial scenarios, like someone trying to cheat in a Lightning channel using these new time locks. Developers really had to put on their black hats to find flaws before they could be exploited.
And these weren't rolled out alone, right? You mentioned a bundle.
Correct.
Yeah.
They were bundled together with another important related upgrade called BIP-113.
What does that do?
BIP-113 basically standardized how median time passed timestamps were handled, making time calculations more reliable and robust across the network. So this whole package, BIP-68, BIP-112, CSV, and BIP-113 became known collectively as the CSV soft fork.
And that activated when?
That activated successfully in mid-2016.
Now, I think I remember reading something about a bit of a conflict or complication during the signaling phase for these.
Ah, yes, there was a notable situation. It highlights the governance challenges, the way miners were initially supposed to signal their readiness for BIP-68.
How did that work?
It used a mechanism called is-supermajority, basically checking the version number of mined blocks. But another proposal was being considered around the same time, BIP-109.
That was one of the block size increase proposals, right?
It was. And unfortunately, both BIP-68 and BIP-109 initially planned to use the same signaling mechanism, which obviously created a conflict. Miners couldn't easily signal support for one without potentially being misinterpreted as supporting the other, or vice versa.
Yeah, that sounds messy. How did they resolve that?
Well, it highlighted a limitation in that older signaling method, especially when you have multiple potential upgrades happening concurrently. It actually spurred the adoption of a much better, more flexible system called BIP-9.
BIP-9 version bits.
Exactly. BIP9 allowed different soft forks to each have their own dedicated bit within the block version field for signaling. Miners could independently signal readiness for multiple different proposals simultaneously. So that little conflict actually led to a more robust governance tool for the future. A bit of a growing pain, you could say.
Interesting. Okay, what other practical, maybe less dramatic challenges cropped up?
Another really key one was just ensuring network-wide relay.
Meaning getting the transactions passed around.
Yeah, remember, BIP-68 required transactions to use version 2 or higher, but by default, many Bitcoin nodes back then weren't configured to relay transactions with versions higher than 1.
Oh, so even if you made a valid BIP-68 transaction, it might just get stuck, not reach the miners.
It was a real risk. It wouldn't propagate across the peer-to-peer network efficiently. So this required coordinated updates to the default settings in the Bitcoin core software and other implementations to change those relay policies. Everyone had to agree to pass along these V2 transactions.
A logistical hurdle.
Definitely. And there was also a lesson learned from a slightly earlier soft fork, BIP-65, which introduced UPI lock time verify for absolute time locks.
What was the lesson there?
With BIP-65, some miners had started signaling readiness before the actual software support for enforcing the new rule was fully implemented and deployed in their own mining setups.
Oops.
Yeah, it caused a bit of confusion. It really underscored the importance of miners not just conceptually agreeing with an upgrade, but actually understanding it, implementing a code correctly, and being technically ready to enforce the new rules before they signal. You need the whole ecosystem ready.
Makes sense.
Yeah.
Software readiness has to match signal readiness.
Exactly. And of course, BIP-112, the CSV part, was completely dependent on BIP-68 being successfully implemented and those V2 transactions being relayed properly. They were tightly coupled.
Right, a whole chain of dependencies. It sounds like a delicate operation getting these things live. So how did these specific proposals, BIP-68 and 112, navigate that complex Bitcoin governance process to actually get adopted? Was it controversial?
You know, compared to the really intense, almost political battles around block size increases happening in the same era, the CSV soft fork activation was, well, relatively smooth. It generally followed Bitcoin's standard established process for soft forks.
Which emphasizes technical review and consensus.
Absolutely. It's a process that really prioritizes careful consideration over speed. It involves several key stages.
Okay, like what?
First, the BIPs themselves, the written proposals, were put out there publicly. Then they went through intense scrutiny and commentary, primarily on the main Bitcoin dev mailing list and also in IRC channels, online meetings.
So developers everywhere kicking the tires.
Oh, yeah. Developers from all over the world meticulously picked them apart, looking for any potential security holes, weird edge cases that might cause unexpected behavior, implementation flaws, you name it.
You mentioned they even debated the name, check sequence verify.
Huh, yes. Even the name got discussed. Was it clear enough? Could it be confused with something else? That level of detail is pretty typical.
Very thorough. What came after the review?
After that initial period of refinement based on feedback, developers created public test versions of the software. Reference implementations were built so people could experiment and verify the code.
Testing in the wild, sort of?
Kind of. And then came that crucial phase we talked about, miner signaling, using the BIP9 version bits mechanism.
And the threshold was high.
Extremely high. For the soft fork to lock in and then activate, 95% of all the blocks mined within a specific 2-week difficulty adjustment period had to signal support. 95%.
Wow, that really forces broad agreement.
It does. It reflects Bitcoin's deep-seated conservatism when it comes to changing the core protocol. You need overwhelming consensus.
So while CSV wasn't maybe as dramatic publicly as, say, SegWit or Taproot later on?
Right. It didn't have the same level of public fanfare or controversy, but the process itself revealed some really important dynamics about Bitcoin governance.
Such as?
Well, it reinforced the community's preference, generally, for smaller incremental improvements, especially ones where there's clear, broad agreement among the technical experts. Things that are seen as clear wins without major trade-offs.
Less contentious stuff.
Exactly. And it really highlighted, again, the importance placed on backwards compatibility, the soft fork approach, and making these new features opt-in, like using transaction version 2. Users and miners choose when to adopt.
It wasn't forced on anyone.
Right. And in many ways, the relatively smooth process for BIP-68 and 112 kind of set a precedent. It informed how later soft forks, like Taproot or discussions around things like covenants, were proposed, debated, and eventually approached for activation.
So it helped refine the playbook for future upgrades. Less confrontational, more collaborative?
I think so. It really showcased the collaborative nature of the ecosystem when things go well. You had developers designing and building, miners who were generally supportive, likely incentivized by the promise of better scalability and maybe future fee growth from layer 2 solutions like Lightning.
In users?
And users, or at least the vocal parts of the community, who were excited about the potential for faster, cheaper transactions. And you can't forget the BIP editors.
What role do they play?
They play a crucial, often unsung role in just managing the process, making sure the proposals are clearly written, properly formatted, assigned numbers, and basically acting as librarians and quality control for the improvement process.
Keeping things organized.
Yeah. So ultimately, after all that review, testing, and signaling, the CSV soft fork successfully locked in around May 2016 and officially activated on the network in July 2016. And by all accounts, the actual deployment was remarkably smooth. No major hiccups.
That smoothness really speaks volumes about the thoroughness of that whole process, doesn't it?
It really does. When the preparation is done right, the execution can be quite seamless, even for consensus changes.
Okay, so let's fast forward. We're years past 2016 now. What's the real, tangible, long-term impact of these two, seemingly small technical changes? How have BIP-68 and CSV actually changed Bitcoin's capabilities and its future outlook?
Well, looking back now, with the benefit of hindsight, they were genuinely transformative, absolutely revolutionary in their own quiet way.
How so? What's the biggest impact?
The most direct, most visible impact, of course, has been enabling the practical development and, importantly, the growth of the Lightning Network.
Right.
Today, Lightning is facilitating potentially millions of Bitcoin transactions, often with incredibly fast, near-instant speeds and really negligible fees.
A different world from on-chain fees sometimes.
Totally. And it's grown into a significant network in its own right. You've got tens of thousands of public nodes, something like 80,000 channels connecting them, maybe more now, and a total capacity holding thousands of Bitcoin.
It's substantial.
It is. It's really starting to deliver on that original vision. Near-instant, low-cost Bitcoin payments, making Bitcoin far more practical for, smaller everyday transactions, coffee, remittances, things like that.
Yeah, it's amazing to see Lightning actually working and growing. But you said these BIPs enabled more than just Lightning, right?
Oh, absolutely. That's key. BIP-68 and BIP-112 provided the essential building blocks for a much wider category of Layer 2 protocols and other smart contract constructions on top of Bitcoin. It wasn't just about Lightning.
Like what else?
Well, we're now seeing active development, experimentation, even deployment in some cases, of things like watchtowers.
What do they do?
They act kind of like guardians for Lightning channels, helping ensure fair play if one party tries to cheat while the other is offline. Then you have ideas like channel factories, which could allow for the efficient creation of potentially many, many payment channels with just a single on-chain transaction. Very efficient.
Interesting.
And even more advanced concepts are being built using these primitives. Things like discrete log contracts or DLCs.
DLCs, heard of those.
Yeah.
Complex financial contracts on Bitcoin.
Yeah, enabling complex financial agreements, futures, bets, insurance to be settled using Bitcoin, but without revealing all the sensitive details of the contract to the public blockchain. Very private. Plus other things like submarine swaps, ways to move Bitcoin between the main chain and layer 2 seamlessly. State chains, payment pools, even just simpler two-party bidirectional payment channels that aren't part of the full Lightning Network routing system.
So it really just cracked open a whole new design space for innovation on top of Bitcoin's base layer.
That's exactly it. It opened the floodgates for building new capabilities. And culturally, it fostered this really important mindset of script extensibility within the Bitcoin development community.
How so?
It proved that you could add powerful new features, powerful new functionalities without resorting to contentious hard forks.
Which can split the network.
Exactly. Instead, the focus shifted to adding small, well-understood, composable primitives like CSV through soft forks, minimal changes that unlock maximum potential.
Small hinges swing big doors.
That's a great way to put it. The success of BIP-68 and 112 really validated this strategy, making small surgical upgrades that enable outsized capabilities, and that approach has pretty much become the norm for Bitcoin development since then.
You can see that in later upgrades.
Definitely. You look at SegWit, you look at Taproot, and the introduction of Schnorr signatures. They followed very similar principles. Careful design, soft fork deployment, unlocking new potential without breaking compatibility.
So these BIPs didn't just enable Lightning, they kind of showed the way for Bitcoin to evolve.
I think that's fair to say. They demonstrated that Bitcoin could evolve, it could adapt to meet new challenges like scaling, without compromising its fundamental properties, that security, that decentralization. It really solidified this idea of a layered approach.
Layered scaling.
Yeah, the base layer, Bitcoin's blockchain, focuses on being that rock-solid, incredibly secure, decentralized settlement layer for large value. Then functionality, complexity, high transaction throughput that gets pushed to higher layers, like Lightning, built on top.
Using tools like CSV.
Using tools enabled by things like CSV. And this success continues to inspire more research and development. People are working on making Lightning channels even better with things like channel splicing, or exploring even more advanced smart contract ideas that might be possible now.
It really feels like they laid a critical foundation stone, and now people are building all sorts of amazing structures on top of it. I remember seeing a quote from Joseph Poon, one of the Lightning Network co-creators.
Oh yeah, he made a really insightful point early on. He talked about how off-chain networks, like Lightning, essentially shift the scaling bottleneck.
How?
Instead of the limit being the number of transactions that can fit in a block, the limit becomes more about the number of users who need to open or close channels on-chain.
Ah, so it changes the nature of the constraint.
It's a profound shift in thinking about how Bitcoin can scale globally. Fewer on-chain footprints needed per user, potentially. So yeah, ultimately, these seemingly tiny technical BIPs, they truly cemented Bitcoin's ability to evolve beyond just peer-to-peer electronic cash into something much more versatile, a programmable, scalable, global money system.
So to wrap up then, these two changes, BIP-68 and BIP-112, they weren't just minor tweaks. Not just bug fixes.
Not at all. They might sound dry, maybe a bit obscure if you're not deep in the weeds.
Yeah, the names aren't exactly catchy.
No. But they were genuinely foundational upgrades. They directly enabled the Lightning Network we see today and this whole growing ecosystem of other off-chain innovations. They were a direct answer to Bitcoin's big scalability questions back then.
It's just such a powerful reminder, isn't it, that not every huge breakthrough comes with flashing lights and big headlines. Sometimes the most significant, most lasting changes come from these smaller, quieter, but incredibly well-designed additions deep down in the code. The plumbing.
Absolutely. These perhaps unsung upgrades, they're a crucial part of Bitcoin's story. They show its amazing ability to scale, but to do it trustlessly on its own terms, keeping those core principles intact.
It really makes you wonder, doesn't it?
Yeah.
You know, how many other seemingly small, maybe unnoticed technical foundations are out there? In other fields, not just crypto.
Yeah.
Foundations that might be just as crucial for future innovations we can't even properly imagine yet. It really drives home how important it is to understand those underlying building blocks, even if they aren't the glamorous part.
Definitely food for thought.
Oh, so maybe a final thought for you, the listener. What other technical foundations, maybe in Bitcoin, maybe in other technologies you follow, do you find most fascinating or maybe most consequential, and why? Definitely something worth pondering.